Hello everyone! Today we are talking about graphing our trig functions. So remember, these are functions. We initially introduced them as the ratios in right triangles of various sides over various other sides, but they are also functions where the input is going to be some angle measure and the output is that trig ratio. So we're going to focus in this video on graphing sine, and in subsequent videos we'll talk about cosine and tangent. So let's talk about what is the parent function for sine. The parent function is just y equals sine of x. You might also see that as y equals sine of theta, which generally just means you're going to have a theta axis instead of an x-axis. But in either case, either theta or x, those are going to be your inputs or your angle measures. So my recommendation is as you're following along to I include these tables. Take a moment perhaps to pause the video and copy these tables into your notes, and also have some graph paper handy. When I'm filling out this table, I will be relying on the unit circle, or my knowledge of the unit circle. So as just a quick reminder, in our unit circle, if I've got, let's maybe sketch that here. Well, let's say that's a perfect circle. Let's say I've got some angle and it goes through some point. And I know this reference angle is theta prime, and the coordinates are some x and some y. So our x, well, that tells us the cosine of our angle, where our y tells us the sine of that angle. So if we're looking at perhaps a filled in copy of our unit circle, it's going to be our y values that we are interested in. Now, I chose not to necessarily copy all of the values of my unit circle into my table here. I'm only going in increments of pi over 4, or 1/4 of pi, or if we're talking about degrees, 45 degrees. And that's just because I feel like that gives us enough information. So that's simply a choice I decided to make. Now, in general, I'm going to be talking about radians as opposed to degrees, but I do, as you can see, have all the degree measures listed here as well. Okay, so let's maybe start with filling out our table. So we're asking, of course, for our y values, what is the sine of that particular angle measure? Y is equal to the sine of x. So the sine of 0 is where I'm starting. Well, the sine of 0 is 0. Again, if I'm looking at 0 degrees on my unit circle, the coordinates there are 1, 0. 0 being the y coordinate that I'm interested in for the sine value. So I'm just going to take a moment to fill in the rest here. We'll notice some repeating patterns, or repeating values, that is. Square root of 2 over 2, 1, square root of 2 over 2, 0, negative square root of 2 over 2, negative 1, negative square root of 2 over 2, and 0. Okay, so in this first table, what have I really covered here? I've gone from 0 degrees, or 0 radians, to 2 pi radians, or 360 degrees. This is one full rotation around my unit circle. All of the other angles that I would be looking at would be coterminal with other angles from this first rotation. So I'm just going to call it out right now. Sine is going to end up being a periodic function. So will cosine, and so will tangent. Okay. So same idea, I'm going to fill out the other table that I have representing all of the negative radians, or negative degrees. So we'll have 0, negative square root of 2 over 2, negative 1, negative square root of 2 over 2, back to 0, Now positive root 2 over 2, positive 1, root 2 over 2, and back to 0. So a lot of repeating values, certainly. Okay, so let's think about how to turn this into an actual graph. Now we got to think about our scale for our axes. So I went from 0 to pi over 4 to pi over 2 to 3 pi over 4. I chose these increments of basically fourths of pi. So I might mark on my x-axis, or we could also call it our theta axis, I might mark that every 4 increments is pi, meaning 1 increment is pi over 4. I'm just going to choose not to draw or write all of those out just because I think it will make my x-axis really crazy. So I'll just count another 4 and label that as positive 2 pi. So I'll label my negative side in the same way. And here's negative 2 pi. Okay, so what about our y-axis? Well, first of all, what is the square root of 2 over 2? Let's maybe think about a decimal approximation for that, because I don't know without a decimal really where to put that y value. Well, it turns out this is about 0.7, so that's still less than 1, meaning 1 and negative 1, those are kind of my like minimum and maximum values. So I don't think I want to go in increments of just 1 on my y-axis. I'm going to maybe space it out a little bit, have some room. So I'm going to do a similar thing. I'm going to count up 4 and say, here's positive 1, and down 4 and say, here's negative 1. Okay, so let's maybe plot those points, starting with our 0, 0. All right, next would be our pi over 4, and that's root 2 over 2, which is about 0.7, so we'll say that's about here. Okay, next we're up at 1, back down to about 0.7, crossing the x-axis again, interesting. Then we're going down to about negative 0.7, negative 1, negative 0.7, and then back to that x-axis. Okay, I'm going to plot my negative points as well before we move on. Okay, so hopefully this is about what you've got on your paper. So we are going to try to avoid doing this, just like connecting with straight lines all of these points. In general, these trig functions, in my opinion, are really beautiful. They are these kind of gentle curves, and I'm not the best at drawing them on my computer, if I'm being honest, but they're kind of like this. I sort of have to separate them out. Looks kind of like that. That's still a little pointier than I would prefer. In general, we're kind of aiming for something like this. That is what our sine will look like, is these repeating kind of curves. We call this the sine curve. So give yourself a little bit of practice. Have patience with yourself, certainly. Try to avoid making them super pointy, but it's something that requires practice, certainly. So as I said, these are periodic functions. So being a periodic function, that means we can define, especially for our parent function, the period and what one cycle looks like. So the period, how long it takes for us to complete one cycle, or the horizontal length of one cycle, is 2 pi. Now, I would say it's 2 pi because my graph is in radians, but we could have also made our graphs in degrees instead, which would mean our period would be defined as 360 degrees. also a full rotation of the unit circle. That is no coincidence. Okay, a cycle, as mentioned, looks like this lovely little curve. Again, we're trying to avoid making ours super pointy. And now, though, we want to talk about how these graphs can be transformed. Because this is just what the parent function looks like. It's going to look a little different if we start maybe multiplying our function by different values. So let's give ourselves kind of a format for those transformations. And this is what I mean here. Y is equal to A times sine of B times theta. Again, theta, or we could say X there. So A is going to represent the amplitude of our graph. And let me just talk about what our amplitude is. So again, we'll just sketch roughly our sine curve, one cycle of it. So our amplitude will be half the difference between our minimum value and our maximum value, which often is going to correspond directly to sort of the height of one of these curves. Now, we always talk about amplitude as a positive number, which is why we see our we're taking the absolute value of A to give the amplitude. So that's our amplitude. We can see if we multiply that by, 12, we'll have a much higher amplitude than our parent function. And just by the way, in our parent function, it may be helpful to include this in our notes. A is equal to 1 and B is also equal to 1. Okay, so the period is affected by B. So the period is given by now 2 pi divided by, again, the absolute value of B, so just the positive version of whatever that is. So, for example, in our parent function, when the B value is just equal to 1, our P is 2 pi divided by 1, or just 2 pi. However, if we were to say, look at the graph of y equals sine of 2 times theta, well then our period there would be 2 pi divided by 2, or just pi, which tells me the length of a full cycle, both that like up and then back down and curving up, that would all happen in just pi radians. So I maybe want to just quickly compare what that might look like. So back up at this rough sketch of my parent function, we'll say that this is not 12, 2 pi. 2 pi, can I erase that? There we go. So halfway there, where I'm crossing the x-axis again, that's pi. Meaning if I were to graph this other function, y equals sine of 2 theta, right on top of this, I'm going to do another of those sine curves, but all before I get to pi. So let's see if I can sketch that. Okay. So I might even sketch the next one. There are really 2 cycles occurring in 2 pi radians. So I often think about B in that way. I'll say, well, in 2 pi radians, whatever B is, that many cycles are occurring. Let's think about how then we could graph this example. Y is equal to 3 times theta. So that, if just based on what we were just talking about, B is equal to 3. So there are 3 full cycles, that up and down kind of pattern, in 2 pi radians. Another way of thinking about that, of course, is by finding our period. So we can say P for period is equal to 2 pi divided by 3. Well, that doesn't actually simplify at all. 2 pi divided by 3 that's kind of it. Okay, now let's see. How would I go about graphing this? Well, I just said that there are 3 cycles occurring within 2 pi. So I might think about dividing 2 pi into thirds. I'm going to write that down. Divide 2 pi into thirds. So what I mean by that is, okay, from 0 to 2 pi over 3, one cycle is going to occur there. One cycle will occur. Then from 2 pi to, okay, what's the next third? From 2 pi over 3 to 4 pi over 3, there's going to be another cycle occurring. And next from 4 pi over 3 to 2 pi, that's our third cycle. So I could graph this a couple different ways. I'm going to graph it to show basically all 3 of those cycles first, and then I want to talk about maybe a slightly easier way to graph it. So again, I'm going to use the same scale, 1, 2, 3, 4, here's pi, 1, 2, 3, 4, here's 2 pi. So I know I'm trying to squeeze in 3 cycles in that space. So let's get an idea of where my various kind of border points are here. So starting with 2 pi over 3. So I'm going to estimate, okay, what is about 2/3 of pi? So maybe about here-ish would be 2/3 of pi. Okay, now my next border point would be 4/3 of pi, so maybe about here-ish. Oh, where'd my other point go? There we go. And maybe I'll do the same cycle, or the same, same scale for my y-axis as we did before. So up 4, that's going to be 1, down 4, that's going to be -1. Of course, I kind of jumped over this, but our amplitude for this equation is still just 1. We haven't changed a. So let's see if we can sketch this. We know we start right here at the origin. We're going to go up to 1. Ooh, barely kind of fit that in. Let's see if I can squeeze this in. Now this is definitely not perfect, but that's about what this graph would look like. You can see our sine curves are much tighter than they were before. It kind of looks like a heartbeat on the picture if you ever watch medical shows. So that's one way to go about graphing this equation. Now another way that I feel like is a little bit easier is to maybe change the scale on our x-axis. We know that one cycle occurs, again, in 2 pi over 3. That's our period. So I'm just going to sketch this off to the side. I'm going to mark that here is my 2 pi over 3. Here's 4 pi over 3, because I generally want to plot at least 2 cycles. And I want to plot kind of the important points here, which would include my x-intercept, so I know when I complete that cycle, I'm crossing the x-axis again. But you know what? Halfway through, I'm also crossing the x-axis as I start turning around. So I have a bunch of different x-intercepts that I can plot here. And that one's not quite halfway, but we'll call it okay. Now the other valuable points are my maxes and my mins. So if I say up here is 1 and down here is -1, then I know for this graph I'm going to go up to my max and then down to my min. Where did my max point go? There we are. Then back up to my max and back down to my min. So I might just then fill out as best I can my lovely sine curve and just go with those kind of key points. Again, the x-intercepts, the max, and the min values. So we generally want 2 cycles when we are graphing these functions, 2 cycles. So I find this to be way easier than doing this. This involves like dividing 2 pi into those even increments and then trying to like squeeze in your sine curve, even then it might not make sense. So this is what I would generally prefer to go with. Okay, in the next video we will talk about cosine. Thank you, everyone.